So we would say that a is the base, and then the independent variable x is in the exponent, and of course the dependent variable is f of x, which is the same thing as y. A has to be positive, and then a cannot equal 1. If that were the case, you'd have 1 to the x, any value in the exponent. If 1 is the base, is just 1, so that wouldn't be an exponential function, that'd just be y equals 1. The domain is all real numbers because there are no values for the independent variable that cause division by 0 or negatives under square root. And as we will see on the graph in just a second, the range is strictly greater than 0 to infinity. So we do not include 0. The reason for that is no matter what real number we put in the exponent of a base, we can never equal 0. So an exponential function is asymptotic at y equals 0. So the graph will flatten out at y equals 0, get really, really close to it, never touch it. If we plug in 0, so this is the y-intercept, f of 0 is just another term, is synonymous with y-intercept. If we plug in 0 into an exponent, in the exponent, 0, any base to an exponent is always 1, so like 5 to the 0 power is 1. So the y-intercept is going to be 1. If we have a fraction, so that's what this says right here, is if a is strictly between 0 and 1, such as 1/2 to the x, the function will strictly be decreasing, and if a is strictly greater than 1, so something like f of x equals 2 to the x, the function will be strictly increasing. What that tells us about strictly decreasing, strictly increasing, there are no relative extreme values if the function has no turning points and things like that. So we can graph these using graph shifting properties, and we can always plot points, and we're going to plot ordered pairs on the next page. But if you recall the graph shifting properties, you might need to look back to 2.6, how to shift a graph left, right, up, and down, reflect it across the x-axis, and reflect across the y-axis. So here's an example. If the function is 2 to the x, we need to graph negative f of x plus 3. So this plus 3 is a vertical shift of 3, and the negative out front here gives us a horizontal reflection, so a reflection across the x-axis, because negative f of x is the same thing as saying negative y. The opposite of the y values would flip the graph over the horizontal. So here's the graph of f of x equals 2 to the x. Then we are going to shift that up 3. So that would mean we would have an HA. Now, the HA was at y equals 0, the horizontal asymptote. So if we shift up 3, that would mean the HA would be at y equals 3. The negative out front is going to flip horizontally, reflect horizontally, which would then give us a y-intercept at 0, 2. So let's take a look at finding some ordered pairs. Here's 3 to the x. 3 to the negative 4th is the same thing as saying 1 over 3 to the 4th, which is 1 over 81. 3 to the negative 3rd is 1 over 27. 3 to the negative 2nd is 1/9. 3 to the negative 1st is 1/3. 3 to 0 is 1. Then we have 3 to the 1st, 3 to the 2nd, 3 to the 3rd, and so on and so forth. So we could plot all of these on the graph. Exponential functions are all going to have the same shape. It's more or less, how fast is that graph going to start compounding over here depends on, how large that base is. But so we're still going to have a y-intercept at 1. We still have an HA at y equals 0, and we can plot all of these points on that exponential curve. Okay, the property in the real number system is that if we have a base to an exponent and we know that equals the same base to an exponent, those two exponents have to be the same. So for example, if we said something like 2 to the 4th equals 2 to the x, then we know that 4 has to equal x. There is no other way for x to equal anything else but 4. So we can solve exponential equations using this property of real numbers simply by rewriting the base, if possible. We will get into a section in a little bit where we're solving equations where it's not possible to rewrite the bases as equal, and then we will do a different technique. But on this one, we realize that 9 is a power of 3, so we can rewrite 9 as 3 squared. And this is a good time to say that we need to make sure we are solid on our intermediate algebra properties of exponents in order to be proficient with exponential functions and equations and that type of thing. So an exponent to an exponent, we're going to multiply those together. So 2 times 2x is going to be 4x. Now this is true if and only if x plus 1 equals 4x. So 1 equals 3x, x equals 1/3. Okay, compound interest. Now this is a pretty important topic, out in the real world, and it's not just for your savings account or something like that. Anytime you have a percentage change that compounds, using this exponential function, can help you understand that. A lot of times we misinterpret models to be linear when in fact they're exponential. The difference is not necessarily subtle in terms of outcome. So just starting with the basic compound interest formula can really help you understand exponential functions, and then when we get into applications of exponential functions in 4.6, we will go more in depth with compound interest and other forms of applications. But we're introducing the formula now. So this is a specific formula in finance, so we're using specific letters and terms, but this is an exponential function. Let's take a look at A is the future amount, and A is the function value. So this is the dependent variable. P is the principal, which is the initial amount, which is the same thing as saying P equals f of 0, the initial amount. So that's the value when t is 0. Interest rate is given as a decimal between 0 and 1. I guess unless you have an interest rate beyond 100%, but still write it as a decimal. And n is the number of times compounded annually. And then the independent variable, is time. Excuse me. So we are going to input different values for time, and we're going to fix r and n and p, and then the dependent variable amount is going to change over time. Now you could examine this interest formula where, say, something like r was the independent variable, and in that case time would then be fixed if we're doing single variable, but it's most common to analyze this where t is the independent variable. So like 1 one lender is offering a 3.5% mortgage for 30 years, and the other one's offering a 3.25% fixed rate mortgage for 30 years. You could compare those two and see how much you save over time and the amount and things like that. So this first example, 1,000 is deposited into an interest-bearing account paying 4% interest compounded quarterly. Now quarterly means once every 3 months, which would be 4 times a year, so n equals 4. And we're going to find the interest earned in 10 years. So we're not graphing the function, we are simply using the formula to compute this exact scenario where r is 0.04, t is 10, and n is 4. So substitute those into the formula, carefully type that into your calculator, and you're going to get approximately $1,488.86. Another useful way to look at this is a present value analysis. So if you keep in mind, let me pull this back up. If you keep in mind that A is the future amount and P is the initial amount, we can examine, in this situation I've got an example that allows us to take a look at the present value of $10,000 cash in 25 years. So that cash has suffered from decreased value from inflation. So let's take a look at that. We're going to assume a 2% annual inflation. And that's pretty common, and the Federal Reserve actually tries to stick to 2% inflation. Now, you can pause for a second and look up what inflation is, but a pretty basic way to understand inflation is that over time the costs of goods and services increase in price. That's the same thing as saying the value of $1 decreases. So the purchasing power of the dollar is a strictly decrease. It generally, over the course of time, is going to be strictly decreasing. Cash is an inflationary asset. It is not deflationary, meaning it does not go up in value. Cash goes down in value. So we're going to suppose that we take $10,000 cash and we're going to just put it in the safe. We're going to lock it away for 25 years. So it doesn't matter what year we start in, because we're going to end up examining the value of that $10,000 25 years from whenever we lock this cash up. So we're going to answer the question, what is the present value of that $10,000 in the 25th year? So in year 25, we're going to unlock that safe and we're going to pull out, we're still going to have $10,000, but we want to ask ourselves, this $10,000 is worth how much money 25 years ago? So this is still the compound interest. Now we're looking at annual inflation, so we're not compounding quarterly like in the last example. So n equals 1, the rate is 0.02, and t is 25. However, the difference here is that we're not taking $10,000 and investing it at a 2% increase. Our amount at the end of this time is $10,000. We want to know what the initial amount would have been to be equivalent to that $10,000. So we know the future amount is 10,000. So we have 1 plus 0.02, that is r over n. and then this is t times n in the exponent, so t is 25. So to solve for p, which is the initial amount, the present value, I'm going to make a note of that. So I'm not going to say the word initial amount again because we are not taking about $6,100 and then investing it at 2% for 25 years to get 10,000. We are fast forwarding to the future, looking at that $10,000 and saying, okay, what was the value of that, you know, at year 0? So to solve for p, we would divide both sides by 1.02 to the 25th. So 10,000 divided by 1.02 to the 25th is about 6,095. So here's the interpretation of this scenario. If you put $10,000 in a safe today and don't touch it, in 25 years from now, it will purchase about the same amount of goods and services as $6,095 would have in the present year. So let me write that down. Okay, so this problem gives us the conclusion that in 2046, if the present year is 2021, in 2046, $10,000 will purchase the same amount of goods and services as $6,095 did in 2021. This is why your grandparents will tell you about, the cost of a gallon of milk when they were little was 50 cents and now it's $5. It's not that the milk has, a gallon of milk has somehow undergone some crazy transformation to be worth that much more. It's not like the product is that much better. It's strictly a function of time under, annual inflation, and that results in the decreased purchasing power of the dollar. So if we bought, something that in 2046 that is worth $10,000, we could have purchased that same thing for $6,095 in 2021. Now, this is on average. It doesn't mean any single one thing. It's inflation is the totality of the increasing cost of goods and services, not just one single thing, such as I gave an example about milk, cost of a gallon of milk, but real estate's a good example. The cost of real estate will continue to rise over the long run, and that's a good example to understand inflation also. So you might have grandparents that say they bought their first house in 1960 for $10,000, and that same house, that same kind of house, might be $100,000 today or something like that. And that's because of the steady, and compounding. It's because of the compounding increase in the cost of goods and services, which is inflation. So this is a present value problem. Okay. And now we're going to talk about continuously compound interest formula. The formula is A equals PE to the RT. A, P, R, and T are as they were in the previous formula for just compound interest. E is a number. It is called Euler's constant. It is an irrational transcendental value that is approximately 2.718. However, I've got this dot 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 because the decimal does not terminate and it has no pattern in the decimal, so that's what it means to be a transcendental number. Most of us have heard of the number pi prior to today. Similarly, pi is probably a more popular transcendental number. E will quickly become one of your favorite numbers because we can do a lot of stuff with Euler's constant, which we will also learn is the base of the natural logarithm. So we're going to take a look back at the same problem we did an example of, where we had $1,000 deposited and was compounded quarterly. So in calculus, you will probably talk about the definition of E. In college algebra, I'm going to give you the approximation, teach you that it is a number. Dr. Leonard Euler, it is named after Dr. Leonard Euler, a historically amazing mathematician. So what we notice is that the compounding, if done continuously, there is a limit. So you might think that if we are continuously compounding that the value just skyrockets. Well, if you follow the original equation from compound interest, if n keeps getting bigger and bigger, so this was 4 times a year, what if it was 1,000, 10,000 times a year? You have the r over n, and then you also have n in the exponent. Well, what that does is it kind of limits how crazy that interest can build up. So if we did that same calculation but continuously compounded, we get $1,491.82, and previously compounded quarterly in the other example, it was $1,488.86. So it is different, and continuously compounded should be more, but you might at first glance think, oh well, if it's continuously compounding, it's going to be astronomically higher. That's not necessarily the case. It's just telling us that rather than saying every quarter we compound the value, it's just all the time the interest is compounding, and this would be the formula for that. Okay, that takes care of 4.2.